Actually, some of you do know me. Those of you, some of you are my students. Others are friends from Islay who've never seen me before and hope they'll never see me again. It's David's actually, you probably, many of you in the island know Dave, but Dave is actually a master's from Stockholm University. So he's actually Swedish. He has a long career behind him, working in industry. He's also an outstanding geologist. I met Dave on the island many, many years ago. And Dave was, for those of you who don't know me, I take student groups around the islands and try not to get them killed. I met Dave many, many years ago, and he's been my teacher on this island. He is just a fountain of knowledge. And he's going to be talking with us today about the greatest glaciation that ever happened. And this is it's a hugely important topic. We're living in a climate that is changing incredibly quickly. And one of the ways we learn about what will happen and what can happen is by looking into the past. The rocks have amazing secrets that tell us what can we, how fast can the climate change? How bad can it be? How extreme can things happen? And the rocks in Islay have a fantastic record of that. And Dave is a real expert on this. And we'll look at he's going to tell us about his experiences. And judging from the picture, he's actually going to take us to more than one island. That does not look like Islay there. That looks like a close by island, which is also very nice. What's the hand for Dave?
Very humble, because he taught me a hell of a lot. That's lots of geology I never knew about. Hard rocks. I was a soft rock geologist. He looked at oil and sandstones and soft rocks. Now also looks at hard rocks. He has a bigger hammer than me, and he helped write the book. So he's been a bit humble about his knowledge of it. So this is, as Alistair says, that's not Islay. Those in the background. These are the Garvellach Islands in the south of Lawn. We're going to be looking at them and Islay as well, because the Port Askaig Formation, named after Port Askaig, obviously occurs on the island here, obviously, and quite spectacularly on Port Askaig in the Garvellach Islands. The reason is that they're exposed there to the west and the waves and the wind, and they get cleaned by the weather, whereas on Islay they're on the east side and covered in heather and grass and all sorts of bracken, and you can't see them so well. But on Garvellachs, they're really cleanly exposed. So we'll take it there. Some of you may have been there. I mean, perhaps many people haven't, but we'll have a nice trip there. This is really a collaboration, this whole research project we're involved in between a whole lot of people. So I'm just presenting on the results of the work of many researchers, Stockholm people included. There's Alistair, Patrick Casey from Stockholm, Martin. The leader of this gang of thieves is Tony Spencer, who I've highlighted in yellow. Tony's the most agile, able, 80-plus-year-old I know, who can leap over rocks like a goat. This is up on Garvellach, the north part of Islay, with some of the, and we've got a team assembled with all sorts of disciplines. They've got geochemists, we've got sedimentologists, we've got glaciologists who know the modern glacial story, because this is a glacial deposit, the Port Askaig Formation, millions of years old, but it has a lot of similarities with what we see today in the Antarctic or the Arctic. So we brought in these glaciologists, modern glaciologists, to look at the old rocks, and they tell us about that, and they look at these old rocks, and it helps me tell more about what's happening, as Alistair said, in the current climate crisis we're in. So it all started really with a PhD that this guy Tony Spencer did in the 1960s on here, and he scrambled all over Islay for his PhD in the early 60s. And this is his mentor, Wally Pitcher. This is what geologists did in the 60s. They went to the Garvellachs in a suit and tie. Now this sort of modern Gore-Tex stuff and boots and stuff. So this is young Tony Spencer in the 60s on the Garvellachs, starting his PhD in 1966. This is Tony a few years ago on the Garvellachs. This is looking down the Garvellachs chain And so what Tony then wrote after his PhD was what we in our team call a memoir. So the Geological Society of London had this memoir series, and in 1971 published memoir number 6 on the late Precambrian glaciation in Scotland, and Tony was the only author on it. The next memoir is coming out this year. That whole gang of thieves and people are going to be all the authors of the new memoir. So Tony got a massive publication coming out in the end of the year to replace memoir 6. Tony's the lead author on that. So this is the new memoir, and it's going to have 16 chapters. So I could stand here for 16 hours and bore you to pieces, because each of those chapters would take me an hour to talk about. So I'm trying to cover the whole of his memoir in a simple, I'm not to be patronising, but in a relatively quick and not too technical tone, and get through some of all these topics. Yeah. I'm going to talk about that. Well, chapter 15. Isabel, where's Isabel? She's not more chapter 15. She's not got anything else to do except chapter 15. Provenance, that means where did these sediments and these clasts of rock. So I've given some samples of granite. These are granites. There's 4 size samples here. Askaig Formation, all actually from where you guys were today at Fionafort. On the sample for Askaig. We do not know where they came from. So the chapter 15 is about what do we know about where they came from, or what we don't know about where they came from. I will rush through quite a lot of this stuff, but I will, because it's my chapter, I will take a little bit of time to talk about where these rocks came from, because it's private. So the Precambrian. So just a bit of geological background. The Precambrian is basically all the time in the world from its formation 4.5 billion years ago, so it is working the scale of time, up to the Cambrian, the beginning of the Cambrian period, now dated at 539. So that's a significant chunk of Earth history. It's divided into sort of all these names. You're used to the names of the younger stuff like Triassic, Jurassic, Cretaceous, all those sorts of names. But when we get down to the Precambrian, we get a whole lot of funny names. Pretty much ignore most of them. But the latest bit of the Precambrian is known as the Neoproterozoic. Those of you doing a bit of archaeology will know about Neolithic, Paleolithic, and Mesolithic, or geologists use the same terms. The Neo is the youngest Proterozoic, and the Meso is the middle Proterozoic, and the Paleo is the old Proterozoic. And that's divided into bits or stages. And what we're interested in is the Cryogenian. And the name Cryogenian gives the game away, because cryo is ice, cold, and it's the period of the Earth's history where it went really cold. And there's a lot of work being done on the Cryogenian period of the Neoproterozoic, of the Precambrian, where the Earth had a lot of ice. In some researchers call this snowball Earth. Some of you may have heard of snowball Earth. It's a period of time, the Cryogenian, when we think the Earth, at least once, if not twice, if not 3 times, froze completely. And the rocks of Port Askaig are one of the best places in the world to see evidence of this frozen world, or frozen worlds, in the Precambrian. So I'm going to take you deep in time to around about 700 million years ago tonight. Yeah, that's where we are. So let's just have a quick, let's just bring into that a little bit closer. So I've turned the thing on its side here, so it's now sideways time. Yeah, so the 539 Cambrian is at the right. Yeah, so life as we know it started here, actually. Before that, it's just slime and bugs and algae and stuff, single cell stuff, not much going on. Really, in fact, most of it probably survived the ice ages just, and then we are all the survivors of the ice age. So that's how we developed the Neoproterozoic further down into these stages here, Tonian, Glaciation, Dikaran. And there are 3, we call them pan-glaciation, because they're glaciations that we believe covered the world, so they're called a pan-glaciation. So these glaciations we believe were at the equator at sea level, and the ice covered the sea as well, so it's and covered everywhere, so we call it pan-glaciation. And there are 3 in Earth's history that we know about now. One called the Stortian, started at about 720. one called the Maranoan. These are names after places in Australia where they were first named. That started and finished about 735, and then there's a wee diddy one, the Gaskiers one, which is not as well known and is not as extensive, but the key ones are the Maranoan and the Sturtian, and for good reasons that we'll go into a little bit tonight, we believe what we have here in our Port Askaig is the Sturtian, and we have the evidence that we have the beginning and the end of the Sturtian, which is very unusual in geology, because usually most of geology is gaps. You see rocks, and there's a great gap. But we think very critically on Islay and the Garvellachs, we are seeing a continuous sequence through the Sturtian, which makes it very, very important worldwide to geologists. And geologists all around the world have come to see the beginning and the end. And we hope that we'll be able to get one of these. Because when we look at rocks in the world, we try and find the place to define the Cambrian, to define the Ediacaran, to define the Cryogenian, and we put a marker in the rock. And it's known as the Golden Spike, which is after the railroads in America where they joined them up. Yeah, they had the Golden Spike. So in Australia, there is a Golden Spike marking the base of the Ediacaran. There's also one in Newfoundland marking the base of the Cambrian, but there isn't one for the base of the Cryogenian. And that's where Port Askaig comes in, because we believe we have a good case here for the worldwide golden spike for the base of the Cryogenian. Not an islet on the Garvellachs, and I'll just show you why. So it just shows how world famous these rocks are. I'm going to quickly talk about snowball. Alice will probably shout me down and tell me I'm talking rubbish, but I'm going to, in 10 seconds, tell you about Snowball Earth. This is a sort of picture that was taken at the time. BBC wasn't good at that time with their documentaries. So yes, ice everywhere is the idea, basically. To get in this state, it doesn't happen very often. It's only happened 3 times, I reckon, perhaps only twice in all of world history. So it's a rare thing. We think it usually had to be cold, and something significant had to happen to turn that very cold state into a super cold state. Yeah. So we think it got very cold. We think it's something to do with the fact that there was a supercontinent there. It was at low latitude. There were a lot of volcanic eruptions at low latitude. They had a lot of sulfate aerosols, all sorts of things. A sort of super perfect storm of things happened. Then we got ice building up, and then we got an albedo effect. We got the sunlight reflected back, and it just got colder and colder and colder, and it couldn't get out of it until things didn't form, because volcanoes know nothing about the ice. They just keep going as volcanoes spew out carbon dioxide. And when you've got to cover the earth in ice, you don't have any weathering of rocks, in which weathering of rocks often brings down carbon dioxide. It's happening today, but too slowly for us. So, but to get out of the snowball, you need a build-up of carbon dioxide. The ice covers the silicate rocks in, get weathering. Eventually, the global heating overcomes it. You get a rising sea level, and you get acidic rain and a big carbonate production. You get things like capped carbonate. So there's a whole lot of things that go on to get a snowball Earth, to get out of it. The Earth has, as I say, only done it once or twice anyway, but that's what we think. So all these things are what we're looking for in the evidence of whether the rocks we see today were a snowball Earth. And we have a thing, a very top of the snowball Earth, I mentioned in the last slide there, called the capped carbonate. And it's most of the Cryogenian successions in the world, we've had this capped carbonate. And the guy on the left there in the slide, the guy with the t-shirt, the vest, is Mr. Snowball Earth. He didn't quite coin the phrase, but anything to do with Snowball Earth has the name Paul Hoffman written across it. And he's a sort of world-famous geologist, and he and Tom and his colleague there, Dan Strag, basically they decided they could see that's a glacial deposit they're standing. It's great big lumps of rock, and that's a glacial deposit, a diamictite. We'll talk about diamictites in a bit more in a minute. It's a lump of rocks and great sizes, great big lumps and clay and sand, all different sizes mixed together. And above it is a limestone, a deep water, warm water limestone. And it's that transition from diamictite glacial deposits to this deep water limestone or the capped carbonate that is very, very, it happens everywhere virtually. There's Yukon, there's Australia, that's Nayural. It doesn't happen here to the same extent. And that's why I want to talk a little bit about that, because it doesn't, we have a carbonate here called the Bunnahabhain dolomite, that don't look like this. Okay, so what does it all look like? This is the last sort of general slide. This is a map of the world 720 million years ago, at the time of the Sturdy glaciation. Look at the ice. One supercontinent on the equator, nothing at the poles. Port Askaig is the yellow star. So we're just south of the equator, with ice at sea level, just south of the equator. So that's the reconstruction we believe that the world looked like 700 million years ago. And the thing called, the red thing in the middle called flip, is the Franklin Large Igneous Province, which we think is the guilty smoking gun, where lots and lots of basalt lava was extruded onto the equator with no vegetation. Remember, plants hadn't been invented, so it's blowing up on the equator, and we think that helped draw down the CO2 and lead to this major cooling event. So the low latitude supercontinent and this flip, which came through, well, got a lot of sulfur dioxide as well, so it came through evaporates and things. So that's the sort of setting of the Port Askaig, and we're sandwiched between old parts of the supercontinent, we're called Laurasia to the north, Amazonia to the west, and Baltica to the sort of east and southeast. So we're in a sort of, all these rocks are deposited in a sort of hole called the depot center between these bits of the continent, old bits of high ground of Amazonia, Baltica, and Laurentia. And that's where the story of these granites comes, because all these rocks that we're seeing here in these granites, are they Laurentian, are they American, or Northwest European? Are they South American, or are they Swedish? So you Swedish geologists, or other Swedish geologists are coming, someone says, oh, look, I've seen that granite, because I want someone to do that. Because I haven't done that. I think I've got some ideas, but I'm going to go through those hopefully at the end of the talk, towards the end of the talk. So let's go to Scotland. So the Dalradian rocks are the series of rocks that occur across Islay and across Northern Ireland, Western Ireland, and extends from Islay north-eastwards up to Portugal. And they're all the rocks that were deposited in and around the Port Askaig Formation around about 800 to 600 million years ago. And they're called the Dalradians. And actually the whole of Islay, apart from the bottom end of the rings, is Dalradian. Yeah, it's got sands and muds and limestones and glacial deposits in it. So they're sedimentary rocks that have been chopped and churned and metamorphosed a bit. And so we're going to hone in on the Garvellachs, hopefully with this slide. Here we are. Here's the Garvellachs up north. Those of you who don't know your geography around here, they're up to the northeast of Islay. There's Jura. This is dominated by the Jura quartzite, which is the bed of rock that's just a bit younger than these glacial rocks. And the brown sort of symbol is the Port Askaig Formation I'm going to talk about. Yeah? And that occurs on the round Port Askaig and a bit inland to the west of Bunnahabhain. So we're going to focus in on the Garvellachs and Port Askaig area. Garvellachs, Port Askaig area. So geologists like to draw a vertical log. It's like an imaginary borehole. You draw all the rocks together, round and flat, and drill a hole through it. This is what, and then open it up. This is what it would look like. And this is what you would, if you drilled a hole right through Islay from Lefroy to the Rins, you would get all those rocks if you could stack them up nice and neatly like a book. So I'm not going to talk about any of these others, apart from the fact that they only have the Port Askaig thing right in the middle. I've coloured it brown. It's right in the middle here. Oops, I'm going to go back because I didn't go too fast. Let's go back to previous. Okay, so we're in the middle of this pile of rocks, yeah? And on top of this pile of rocks, at the bottom, we have the Rins complex, which is 1.8 billion years old. And that is all the sort of pink and green and brown rock you see between Port Charlotte and Port Haven and round to Lossett. And they're 1.8 billion years old. These granites are 1.8 billion years old, but they don't look like the Rins complex. If you picked up some Rins complex rocks, they're not these. Yet you would expect these the granites in, or the rocks in the Port Askaig Formation to be this, because it's the nearest thing. Why wouldn't they be? but they're not. What we have at Port Askaig, some of you who've been out in the field yesterday with Alistair saw what was underneath the thing, the Lossic limestone. And today, some of you came to Bunnahabhain and saw the Bunnahabhain dolomite. I think you students are going to see it tomorrow up on the north coast. So we have limestone, which is coloured blue, limestones, carbonates, coloured blue, each sandwiching this thing. We think most of these limestones below and above the Port Askaig Formation were deposited in shallow, warm water. They've got stromatolites in them. They look like warm water deposits. And where we are on the paleo latitude, the old latitude at the time, just south of the equator, sort of like, it was like the Bahamas. Yeah? And suddenly, everything goes freezing. Yeah? So we have, and then it comes, then the ice finishes and we're back to the Bahamas again. So we have evidence on Islay of what was it like before the glaciation and what was it like after. Nice, go swimming, scuba diving, no fish, but it would have been a nice sort of place to go in a sort of shallow, warm sea, probably. And then suddenly we get this 50 million years of ice age. Let's move on a bit. Okay. So it gets a bit more techie. So the left hand, it's not the left, it's a bit out of focus, but I won't dwell on it too long. On the Garvellachs, we've divided the Port Askaig Formation. Geologists have to split things down into little beds and try out the slivers and things. We're going to splitters. And we've lumped them into what we call member 1, member 2, member 3, member 4, member 5. Members 1, 2, and 3 are on the Garvellachs, and 4 and 5 are Islay. So we have the younger bits. So actually, if you stack them together, you go 1, 2, 3, 4, 5. The younger bits are on Islay, and the older bits are on the Garvellachs. The browns, most of the brown colours there are glacial rocks. They're these diamictites, these mixtures of gravel, sand, clay, boulders that were deposited by the glaciers. And the yellow bits are sandstones, which were deposited in the sea when there wasn't any ice. So you can see instantly from there, it's not all, even though we call it the Port Askaig Formation and it was supposed to be all glacial, there are interludes in there where there wasn't ice, or maybe ice wasn't here, but maybe somewhere else, but it was the sea. So we haven't got a snowball for the whole 60 million years of the Port Askaig Formation. There must have been open water with rivers and deltas and the sea depositing sandstones and limestones and things in the middle of this Port Askaig Formation. So it's not just like the picture with Paul Hoffman on. He's got 50 meters of diamictite in one bed, because that's snowball earth. We come here, there's 48 diamictites. We've numbered them all. Tony Spencer can go up to a rock on Islay and Garvellachs and say D15, D38. You can look at it, he knows, you can see them, because it's all to do with how many granites are in them, what the granites look like in them, and what the other pebbles are in them. We can look at the pebbles and say, because what happens is that the erosion has brought deeper and deeper erosion, and so the early pebbles are all local pebbles, and the younger rocks have got these older pebbles in them. So there's a sort of what we call a stratigraphy of pebbles in the formation, and we get this, and we've divided it into these members based on the sort of these sandstone periods, and we've also got at the top of member 1 some really weird stuff. Can someone just move it? We have 4 very funny rocks in member 1. One is called the Great Breccia. Above that is a thing called a main dolomite. Now, dolomite is a limestone type, a carbonate type rock, which you wouldn't expect in a glacial sequence. The carbonate rock, a magnesium calcium carbonate rock. Then we have a thing called the disrupted beds, which are really weird, and I've got a lot of iron in them. Then we have another dolomite in the middle of that with stromatolites, nice warm water again. Will be nice warm water. So we've shown that the top of member 1 is really weird, and it has lots of different types of rocks in it. And underneath, right at the bottom here, on the Garvellachs, we have the rocks that were pre the glaciation, before the glaciation, and they're on Garvellach, and they're called the Garvellach Formation. And I think I'm going to show you some of that in a minute. And then we'll go to Islay. We'll show some rocks through this member 1, these weird rocks here, up through member 2, member 3, some nice pictures coming up. And then member 4 and member 5 on Islay. So we're just going to go through some rocks, pictures of rocks. But first I'm going to take you to the Garvellachs, just to show you what the geology looks like This is Tony's wonderful map. This is Garvellach's turned right round the other way. And those numbers that I just talked about, 1, 2, 3, are like that. So the Garvellach is nice and simple. The rocks just dip. No folds, nothing going complicated. They just dip away to the southeast at 35 degrees. And the Garvellach Formation, which is the base of the base of the glacial sequence, is exposed here. This is the Garvellach Formation. Is brown, is non-glacial, and then there's the first bit of glacial rocks. Number 1, number 2, number 3, which is mainly sand, and across 3 islands. I'm going to take you to all these 3 islands in the chain. And we have a little bothy here we've used just to base ourselves occasionally. And people who've been to Holy Isle, who may have been there, it's got the best beehive monastic remains in Scotland, because they weren't ever really settled, the islands, after that. So they haven't been cannibalised. So there's these beautiful 8th century, 7th, 8th century beehive cells there that are maintained by Historic Scotland. So if you ever get a chance to go, there's more than just geology out there. Okay, this is Tony standing on the Garvellach Formation with his stromatolites. Stromatolites, these algal mounds, which are very common in the Bunnahabhain Formation. You also get them below the glaciation, telling us this is our Bahamas type sequence, yeah? This is Tony standing on the Garvellachs with his hard hat. There. We also have gypsum. Gypsum is these crystal blades of gypsum that are often associated with hot climate, hot or arid conditions. So probably non-glacial. These nice rosettes. One of your analysis students is about to do a big research project on these things, so very topical to see those nice exposures there. Some nice ones on the north coast of Islay as well. Then this is the only bit of techie bit I'll do. This is what we call a carbon isotope profile, and worldwide, this negative, what we call a negative excursion of carbon isotopes. I'm not going to go into that why it is, but it's world famous because it's called the Islay anomaly. And around the world, geologists talk about the Islay anomaly. And it's often been seen as a temperature proxy. So we get this low or very light carbon isotope signal. And it was thought that was a decrease in photosynthesis because it was getting colder. You would get decrease in, and that would give this carbon isotope. It's probably not as simple as that anymore. Probably a lot more complicated than that. But this anomaly occurs below the Sturtian everywhere across the world. And we've got it here. And it's named after him. And then the first glacial rock of the Port Askaig Formation occurs on the Garvellachs at the top of bed 48. This might be the place that we might want to stick our golden spike. Remember I was talking about the golden spikes earlier? So this might be the beginning of the Ice Age. We've got a periglacial eroded surface. Periglacial means it's been exposed to the permafrost. It's been really, the top of the limestone has been really broken up by the frost and shattered, and it's been sitting out on the open air for a long time, breaking up, and then suddenly a glacier has advanced over it. And we think that change there from this subaerial periglacial environment to a glacial environment is maybe where the Port Askaig, base of the Port Askaig and the base of the Sturtian might be put. Yeah, and we get evidence of glaciers pushing stuff around, folds in the basal part of the sequence. Lots of D numbers. This is D6, D7 with some sandstones in it. I'm not going to go into detail of it. Then we have the Great Breccia D13, which is the one that has huge boulders in it. Some as big as houses, because that's quite big. That's several meters across. This is enormous. This is called the Bowl, and you can imagine it's actually a piece of rock from the Garvellach Formation that's just been shoved by the glacier like a bulldozer. Yeah, that is there's a person there. You see one person? Yeah, this one's enormous. It's not just a little rock in the carpet. This is an enormous great glacier. 50 meters thick of ice actually pushing the bedrock. Yeah, probably permafrost bedrock, pushing it into a fold. That's a complete overfold of rock. Absolutely stunning. And it's pushing everything to the northwest. We think the ice has come from the southeast. That's important when it comes to working out Yeah, this stuff's fun. So this is that picture I showed you at the very beginning of my opening slide, looking down at the Islay with where the monastic remains are. This is the middle island called Cryogenian. Clearly, the geology looks like this. We have the Great Breccia, and above it, I mentioned the thing called the main dolomite and the disrupted beds. They occur here. And down here is a great chunk of rock that's like the bubble. We call it a glaciotectonic raft. It's just a chunk of rock that's just been pushed like a air gale. Something chunk of rock that's just intact, holding in place of it, but pushed by the ice. Like at the top of the Great Breccia, we have a very weird deposit, and one of our modern glaciologists there, Doug, looked at that and said, I know what that is. That is the top of the Great Breccia. There's been a big time gap there. There's been a lot of periglacial time, but the top of that was just out in the open air. Nothing happened, and it just eroded, and there's a bit of creep and a bit of movement down slope of stuff. He said it's a classic place where you've got a big break, and he thinks if we did have a snowball Earth, that's it. There, this glacial deposit that pushed all the rocks around was the sort of last vestiges of the ice that then just froze up. It was huge ice sheets still moving around, pushing stuff about, massive ice sheets, and then suddenly they stopped because everything just froze. The hydrological cycle shut down. Nothing much moved. Anything that was exposed just got frozen for years and years and years, millions of years possibly. So on the Garvellachs, we think we've got this snowball Earth unconformity. And then above it, things start to happen, which is probably the melting of the snowball Earth in some respects, but it doesn't produce the carbonate that Paul Hoffman was standing on. It produces a main dolomite, which is a river deposit, disrupted beds, which are iron deposits. And it's sort of dead straight. This is the disrupted beds. These are iron-rich siltstones. Good at the very end of Iowa, on the top of the hill, down the top of the north side of it. You can take your compass out, it spins. These rocks are magnetic. They've got so much iron in them, they will deflect the compass. You're interested in that, DJ? I'll show you a video of the compass going around and where to go there, because it's really interesting. And I'm not going to go into the detail of the chemistry of that. We think these iron-rich rocks were formed when the ice left and melted across the ocean. When the ocean is covered in ice, we're separating out the atmosphere from the sea, and you can allow iron to develop, and you get this what we call an iron-rich ocean or a ferruginous ocean. And then you may put fresh meltwater into it, and you'll get brine pools with ironstones in them. So again, that's an hour's topic. But we think it's unusual. It gives them evidence that we did have an ice-covered ocean that allowed us to separate the atmosphere from the sea for a long period of time to change the chemistry of the ocean. So when the ice melted, things happened and iron got deposited, because you don't get iron deposits like that since then. Since 700 million years ago, there's virtually no iron deposits like that. So we know when we get those in the Neoproterozoic, they're probably at the end of the Sturtian glaciation. There's no evidence to suggest this is Sturtian, because the Nayural island doesn't have that. And then we get the upper dolomite. This is the funny dolomite that's in the middle of all this glacial rocks at the end of the glacial period, and it's got snowflakes in it again. So it's like, oh, we've gone back to warm water again. So why things happen after the Great Breccia? So the Great Breccia is weird itself, then weird things happen with dolomites and ironstones and stuff like that. I was going to talk about dolomitization, but I'm not going to move on from dolomitization because it's too technical. But what happens at member 2, we define member 2 because rocks go from brown, which is quite dolomitic, the calcium magnesium carbonate, to grey, which has got more carbonate in it. And it changes colour. So there's the upper dolomite. And then it changes to member 2, which is all sort of much greyer. And we have these beautiful, beautiful polygons. Some of you saw some distorted polygons today down at Port Askaig, and some of the students saw that. The Garvellachs, they're not distorted, they're just, this is a bedding surface. There's a lot of flat surface, it's now tipped at 35 degrees, but it was flat. And this was the top of the glacial deposit. The ice melted, left this glacial deposit, diamictite. which then dried out in a very arid climate, we think, and formed cracks, like mud cracks. Yeah, but not, but it was dry, and we think the cracks then were filled with dust from the wind. Because remember, there's no vegetation, the place is brown and no green. So dust, everything, the world must have been very dusty. Any bit of wind blows everything around. Nothing, no plants to hold the dust down. So we think these cracks are filled with dust and sand. And then they were covered up by the sea then rose, flooded it, and preserved these wedges. They taper down, they're like cracks, and they form these sort of polygons. Yeah, and they call it today, you call it patterned ground. They call it, if you go to Alaska and the permafrost of Siberia, they call it patterned ground. The problem is the patterned ground in Siberia and Alaska today, those patterns are much bigger. So the modern glaciologists say, yeah, but don't look like anything quite like today. But the chemistry may be different, the atmosphere different, so there are differences between yesterday, today and 700 million years ago. But you talk to Doug Ben and Mike Hambry and co, they still, it's periglacial. They're wedges, and they're indicating the glacial climate at the time. Then we have things called drop zones. This is where you had open water, maybe a small lake or something. Ice Dam Lake, and in the seasons, it was like one season, winter, it's ice covered, and then the summer it melts and drops any stones that were in it, or rocks into it. You see that on the beds, and so these might be annual cycles. These called barbs. They're called, and they're maybe like tree rings once a year. Yeah, and then suddenly one year, stone drops out, just pops down into the bottom of the lake, but it tells us we must have open water as well. We've got freezing, thawing. This is what's happening after snowball Earth. Our so-called snowball Earth unconformity, our great breccia, bulldozing, periglacial, jelly flux type thing on the top, funny thing. And then we get these iron beds and dolomites and stromatolites. Then suddenly we get more glacial rocks. So it hasn't finished. It's not like the snowball just came and went on Isla and the Garvellachs. It carried on, but in a cyclical way. And that's like the ice age today. It's cyclical. We've got these things called multi-disciplinary cycles. So there's interglacial, glacial periods. We're probably interglacial now. Yeah, and it might come back again because of the way the Earth tilts and the precession and all that sort of thing. So we're seeing evidence in the 700 million year old rocks here of that sort of sort of oblicity of the Earth's axis and all that sort of stuff. We get all these are also very common in modern sediments. These involution folds, they like frost heave, that sort of thing. Yeah, so these valves have been frost heaved. We get all that sort of evidence. We get more wedges, frost shattered stones, frozen sand slabs, all sorts of things that the modern glaciologists. That's what it is. Till Mike Hambry and Doug Ben went there, we didn't know what these were. Just sort of weird glacial rocks. And that's what we see in the dry valleys of Antarctica. All that sort of stuff. We can see all these things beautifully on the tops of these things. And we've got also top of this bed here, we've got conglomerates like this, which is great big lumps of granite all packed together. We didn't know how they were formed. How do you form those? And Doug said, the wind blew all the sand away and the mud away and just left the big rocks so it couldn't blow away. So we call that sort of a lag. These are the big chunks that were just left after the wind had blown all the dust away, which then filled the cracks somewhere else. So it wasn't until the modern glaciologists came along and said, oh, that's what it is. This is obvious. And they looked at this, oh yeah, there's obviously water flowing because these pebbles are lined up. So there's meltwater. So it's not like using snowball Earth all the time. There's got to be water kicking around as well. We found river channels, we found all sorts of other water-laying features within these glacial rocks as well. And we think something like this is the Mackenzie Delta in Alaska, and we think that this is what it looked like when there wasn't any ice, and then ice came over the top of that. And this is what it was like between the ice ages. We had all these little lakes and little rivers and little deltas, and it was very complicated. And that's the Mackenzie Delta size now, and there's the Garvellach Islands. So we're just seeing a little window into something that was probably very extensive. It obviously went from Memoir to Garvellach, so it went from here to Memoir. So we've got, the extension of this area is, would cover that sort of area. So we had a Mackenzie type delta over this area 700 million years ago. And then the ice kept coming backwards and forwards on top of it. If you look north from Dakuli to Garvellach, you see into number 3, which has got lots of sandstones in it. And those are really big tidal sandstones, tidally generated sandstones, but there's still lots of granite. Granite stones predominant. As you go up the succession to number 3, number 4, these things become the dominant thing. And every rock is virtually every rock in D38, for example, is a granite that we don't know where to come from. And there are huge big cross beds. These are cross beds into bed 1 in the number 3. But there's occasional drop stones. These are where these quite big drop stones are coming just out of an ice sheet. And maybe one season, just across this delta, little lakes, and then an ice sheet came over, melted and dropped a granite block into the mud underneath it. So we're going to have a look at later, and we'll go to Ben and Boy, where students were yesterday. Is that right? Yesterday. So these guys will recognise a couple of these pictures. This is the base of the unconformed. This is the base of the Port Askaig in Ben and Boy at Dalradian. It's got this is the Dalradian limestone here, and above it is a big brecciated rock. It's been very, very broken up by ice, and then it's been covered by a sandstone that's filtered down through all the cracks in it. And this is probably the same age as the top of the Great Glacier on the Garvellach, so it's arguably the same unconformity, except we don't have on there all the stuff below it. So the lower part of number 1 is missing on I, and the Garvellach formation is missing. So this is what we call an unconformity. So on the Garvellach, there's a continuous sequence with no real breaks. It's just a rocks just nicely that follow each other. On either here, we think we have an area where possibly this bulldozer effect. Remember I said the guys pushed all these things up into bulldoze it along. Maybe this is a bit that's left behind the bulldoze bit. And so it was all clean and straight, and then just sat there as bare rock for millions and millions of years, and then the water came back on top of it. So I think this is the snowball earth unconformity on Islay, but it's not the place for the golden spike because it's an unconformity. There's a target. Golden spike, you want continuous sedimentation. We get rock stones there. Hopefully, some of you saw this one. You see the beds here, bent by this little dolomite block. That's only that was big. Should have put a scale on it. Bad geologist. Nobody was a scale on his photographs. Probably my finger at the bottom. And you have we have also the disrupted beds, and these are iron-rich beds here. These brown, these blue-grey siltstones are the ones that deflect the magnets. So these again on Islay we have the same as not quite the same rocks, but they're the same. We match them up. We call them the disrupted beds, and we match them up from Garvellach to Islay, and they've got the iron in them. Then above that we get the Port Askaig. You see it we used to be able to see it. We call it covered in a netting, and you get sort of granites. There's a big granite boulder there, nice big pink granite. This is down by the hotel. There's a lot of one holding the door of the hotel. You ever go to the hotel again? Not the sand bar, the main bar. There's a huge chunk of this rock with a very big granite stone in it, holding the door open. So it's named after there, and then there's also at the top of the cutting there. There's a thing called a quartzite, which is this sandstone. And I'm talking about this interbeds of glacial rocks and sand, which is deposited more than the one in the ice. So at Port Askaig, you can actually walk that dangerously at the edge of that road there, and see the glacial rocks and the non-glacial rocks in the cutting there. And then at Fairchild, with some of you today, you probably saw this rock. You'd have seen that rock. This is a classic, nice wave wash bit of diamictite with all these stones in it, the tiny stones, right down to the sand, little stones and big stones, and rocks like this, which is pretty similar to some of these I've got here. What's unusual, I'll come and talk about this, and we won't be talking too much about mineralogy, but the pink there is pink rock, pink crystal in there, and the pink crystal in these rocks here is pink feldspar, very common in granites. This feldspar is incredibly rare and unusual. All the pink granites that are in the Port Askaig Formation have this thing called chessboard albite, which is rare. You won't see it in the literature, but they all have it. You don't get it in the rocks below the Port Askaig. You don't get it in the rocks above the Port Askaig. That's why we don't know where these come from, because we don't know where chessboard albite granites occur in the world today. So you Swedish geologists who've got a task on your hands to find some chessboard albite for me in Scandinavia. Also, this is you crown on the list today, and this is our what modern ways of looking at rocks these days. We take drone photographs. So I'm not going to go into detail of what's on there, but those are the wedges and the things that Alistair was pointing out to you today, where we take a drone picture and then we colour them in. Yeah. So the red lumps are the granites, the yellows are sandstones, and the rest of the rock is the matrix, we call the stuff between the granite stones, so clay and sand. So we try, and we've got faults, which are red dotted lines. So we try and interpret the rocks using things like drones, and we can also rectify it so that all these pictures, we work it all out, the assets from the drone pictures, and then join it all up to make a nice flat picture. So there's a hole in the middle of it, because we didn't get that bit. But it's like a map then. It's not just a sort of oblique picture that could just be at any scale. This is actually can turn that into a real map. And we've done a whole load of drone flights on that coast from the hydro station at the end of Loch Allen right down to Bunafort. And there's a big, at Loch Allen outfall, there's a lovely, what we call a conglomerate. And we've done some ortho photographs of that, where we see these sand bodies going through the conglomerate. So it's all new research. We're working on that. We've got to go back this summer because half the team believe one interpretation, half the team believe another interpretation. Geology is never that simple. There's never a good answer. So this is an intriguing bit of the geology of Islay that we're still working on. We were going to put the memoir out last year, but Tony said, "No, we've got to go back. We need to go back and look at this again and get a government on what we think is going on in the rocks south of Port Askaig." Garvellach, which is the hill to the west of Bunafort, get to the last bit of the Ice Age rocks. These are quartzites with sandstones, not glacial. They're just marine sandstones. But at the very, very, very top of the hill, Tony sent me out and said, "There must be something funny up there." And what you find up there is the very last glacial rock of the Port Askaig. This is purple granite. No one's allowed to hammer or sample because it's, and I always say it's about the size of David Webster's head. And it's a sandstone that's it's a very sandy diamictite, but with just this one lump in it. It says you wouldn't have got that from a river like that. You wouldn't have got that. It's got to be dropped from an iceberg or something like that. And it's purple. It's just weird. It's not pink. It's purple. So yeah, not enigmas. But that's at the very, very, very top of the Port Askaig Formation on Islay. It's everything. And then above that, we get the Bunafort Formation. And you guys are going tomorrow. This is a preview of what you're going to see tomorrow. You Swedish guys are going up there. These are you saw some stromatolites. Maybe some of you came with me to Bunafort today. They're just waving things. They're called cauliflowers. They're like the size of a cauliflower. These are about the size of a tipper truck. Actually, in Fairchild, one of our researchers on the top there. So these are mounds, like imagine bowling coal. You know, that sort of thing. It's on steroids. Sort of huge mounds of these stromatolites. They're just phenomenal, and well worth your visit tomorrow. I hope you get there, you guys, and go, oh wow. These are sort of small ones. These are about a couple of meters high, and they're overlain by a sand bed, which obviously killed them off because they didn't get any further. That sand bed, there's the stromatolite, didn't dome, and this sand bed looks like it sort of suffocated. It went over the top of this one as well. And these are the ones that look like Shark Bay. Some of them talked about Shark Bay today. But these exist today, 700 million years later. That's exactly the model of what we're seeing on the north coast of Islay. That's one type of saline. It's very unusual conditions. Not quite the same as, because at the moment you get stromatolites today, but only where gastropods can't eat them. Because gastropods graze stromatolites, they eat algae. The gastropods hadn't been invented in the Precambrian, so stromatolites ruled the world. Nothing of them. And the very top of the Islay section at the end of Dallas, you get the last bit of the member 4 of the Bunafort Formation, and then you get 5 kilometres duroquartzite. which forms the high ground of Jura and high ground of Islay, and it sits on top. And the very last bit of the course we'll do with Alistair tomorrow, you students, you hopefully will see this transition from the end of the Bunnahabhain Formation carbonate rocks into the Jura quartzite as you climb up the last bit of the cliff. Now, how are we doing for time? This is my bit. I'll take 5 minutes just to, I know it's nearly an hour, but I'll take 5 minutes just tell you a bit more about these granites. And I'll just summarise at the end, so bear with me for a few minutes. Also getting quite warm. Arm waving's hard with us. Okay. So I cut this down. I did this talk 2 weeks ago to the Geological Society of Glasgow. And Alistair just got to keep it simple, because I could spend an hour on this easily, and I'm not going to. Okay, so we get lots of different granites, and I've got some samples here. You can come along after the talk's finished and have a look at these rocks if you've not seen them. But these are all the different types of granites. There's one unusual one. This is called Rapakivi granite, often seen on shop fronts and things like that. It's an ornamental stone and traditionally associated with Finland and Sweden. You get Rapakivi. It's this sort of orbicular granite. It's got these circular type spires like this. Yeah. But often they're mantled. They've got sort of like rings, like tree rings. They've got like a pink one with a green outside. So we have Rapakivi granites in the Port Askaig Formation, and because all those big bulldoze folds came from the southeast and Baltic and Amazonia were that way, everyone was like, oh, Rapakivi granites pushed from the southeast must be Scandinavian. These must be Swedish. That has been the sort of the norm in any of the literature about the Port Askaig really since the 60s. It's probably Scandinavian, but we couldn't prove it because these granites got this chessboard albite in them, which don't really occur elsewhere. I'm not going to go into the technical details. We've sampled these granites, and we think that, so we've done lots of chemistry on them. We understand where most of these granites would have come from, the sort of environment these granites were made in, and what their chemistry was, their rare earth chemistry, their igneous, all sorts of chemical analyses are done to classify different types of granite and where they came from. And again, that's another hour's lecture. But we know roughly where our granites occur in the worldwide lexicon of granites. So we've done all that analysis. And we have this thing called chessboard albite, which is sort of very weird. Yeah, it's weird. You won't find any textbook, but all these prints in here are this weird chessboard albite. And it's a replacement feldspar. It wasn't originally that. We think there's been hot water with sodium in it, probably from seawater, that's taken some of the sodium, some of the potassium out and replaced it with sodium. So it's a sort of what we call a metasomatic feldspar. And it's a bit weird and rare. You won't find it much in the textbooks. But we find it in all the granite in the Port Askaig Formation. And the common feldspar in granites is a thing called microcline, which is nice and Scottish because it's got tartan signature. And one at the top is a thing called microcline. This is chessboard, but it's sort of alternating black and white squares, a bit irregular, but you can get the drift of what's going on here, yeah, with this sort of this sort of checker pattern. But the tartan pattern, the microcline, it's the same sort of, it's a feldspar, it's pink, but it's got this crosshatch pattern of tartan feldspar. We don't see that in the granites at all. Yeah, and we don't see it in the diamictites, but we see it in the white sandstone. So the feldspar story is telling us something about the rocks. It's telling us something really weird, that the granites and the glacial rocks are coming from somewhere completely different from the sandstones. These white sandstones with the big cross threads and the Mackenzie Delta thing that I talked about earlier, that's bringing microcline, Scottish stuff, chessboard, the crosshatch stuff in, and yet the granites have got the chessboard stuff in, will probably come from somewhere else. Weird. And then after that, you never see chessboard albite again. You go into the Geological site and all the rocks are younger than in the Dalradian, never see chestboard albite. You go below the Garvellach Formation, all the rocks are either below the Port Askaig, never, no chestboard albite. Microcline, yes, no chest. So it's weird. So that's just what I just said. Microcline is common before and after. The chestboard albite only occurs in the diamic types. Rocks, these are our samples. We've done dating of these granites to see how old they are. And these are the samples we've got. We've got a Rapakivi that's 1.8. There's a couple of different, the colours are just different studies. But they all cluster around 1.8 billion, which is the same as the rings complex, 1.8 billion years old. So the rings complex is the same age as these. We found one granite, yeah, which is the same when it's actually a bit metamorphic, and we think it's the same age as the Louisian gneiss you get in northwest Scotland. Archean, it's very, very old, 3.2 billion years old. So we know that we know from other studies there must be old rocks there as well as these, but this is the majority of the granites cluster around that. Majority of Sweden's about that age, I believe. Yeah? It's one that clusters around that age. Czechoslovakian, the Scandinavian igneous pockets, a lot of it's around 1.7, 1.8. The Rapakivis in Finland are a bit younger. Rapakivis in Finland are about 1.6. We've got one sample, only one sample we've taken and dated, but it's 1.8. It's older than the Finnish one. So it's got, maybe it's not Swedish. So where are granites or igneous rocks like this? Who are the candidates for it? Yeah. So this is taking you back in a map to 1.8 billion years ago. Scotland's in the middle here. This is North Scotland. This is Northern Ireland. The rest of it didn't exist, hadn't been invented. But there's Rockall. Rockall, the northern half of Rockall is 1.8 billion years old. Southern tip of Greenland is 1.8 billion years old. A chunk of Labrador is 1.8, and a whole chunk of Sweden and Scandinavia is 1.8. And before the Atlantic Ocean existed, and they were all joined together. Yeah, we could walk from here to Labrador. You have to cross Rockall, but Rockall microcontinent, there was no ocean there. It was just all joined up. So all of those rocks were close enough to us here. Yeah, we're here. Rins complex and in the Garvellach is here in the middle of this. So we've basically got Scandinavian rocks to there, right up to the Greenland rocks over this way. So I looked at all the characteristics of the rocks, these rocks, and across the top. They must be 1.8, they must be granites, they must have chestboard albite, they must have this, we won't talk about the anomalies, they'll have all these things, yeah? And they must have 1.8 billion-year-old Rapakivis. And they're all the places I've looked. Scotland, Ireland, onshore, the Rins complex, the rocks in Mayo, offshore, which is Rockall, Stanton Banks. I've looked at the Greenland rocks, I've looked at Labrador, I've looked at Scandinavia, and I've looked at South America. So this is just a very simple table. Traffic lights. My wife will go, oh no, traffic lights. So I traffic lighted that. So if you get a green blob coming up, it means it fits. Yeah. And a red blob means it doesn't. And a yellow blob says I'm not really quite so sure. So this is just going to take you through the blobs, the colours by each of these areas. So the Rins complex doesn't match any of it, right? The Rins stuff and the stuff in Mayo isn't the right age. It doesn't got it's undeformed. It hasn't got chestboard albite. It hasn't got any of them. So it ain't that. Scotland Island offshore. This is Rockall mainly, Rockall area. Not much sample. Rockall microcontinent about as big as the British Isles. It's got about 3 boreholes. It's like trying to tell the geology of Britain from 3 boreholes. And a few dredge samples. So it's really unknown, but we do have a bit of information about Rockall from dredge samples and boreholes. And it's sort of, yeah, but the one sample samples I've seen, thin sections, microcline, not chestboard albite. So the granites, they all look fairly good, but there's no chestboard albite in it. So I thought, it's looking okay, but it's microcline. Stanton Banks has a beautiful undeformed 1.8 billion-year-old granite with microcline in it. Greenland, looking a bit bare. Well, some bits are okay, yeah. What it has got in Greenland is 1.8 billion year old Rappakivi granites. So Greenland, it's the first time on this table that we've got the Rappakivi granite is the right age. And we have some hints of chessboard albite as well. In a few little papers, research papers I picked up, they hint at it, but other bits are wrong. Labrador looking a bit better, doesn't have any Rappakivis, possibly has a bit of chessboard albite. Again, it's not quite so clear. Scandinavia, how was that looking? Pretty good. Pretty much I found some chessboard albite references there, very, very obscure, and a lot of time to find them. Rappakivi granite's the wrong age. I mean, I've only got one sample, 1.8, and most of the Rappakivis in Sweden and Finland are 1.5 to 1.6. So it's a bit, they're a bit young. And what does Amazonia look like? Well, it's pretty good. So South America is a possibility. We have found, I found some references there. Chessboard albite occurs with a lot of tin mineralization in Amazonia, and yet we don't find any tin minerals in any of the granites, or any of the diamictites. So I'm a bit dubious about the South American connection, but a lot of it does kind of match. Now, just to finish off the story, we have this new work that we're just working on right now called detrital zircon. Now, zircon is a mineral that's very heavy, and you find it in sandstones, and it's derived from granites. So these granites will have zircon in them, which is a mineral, and zircon you can date because it has uranium in it. You can date it, and you can get a sandstone full of zircon, little grains of zircon, and you date them all. Maybe there's 150, 200 grains in a sample, and you get a spectrum of ages from them. So this is an example of the Port Askaig Formation. This is old. I mean, you can't really see the dates, but this is old and young. Yeah, and this peak here on this is a granite. This is a Port Askaig rock. The peak there is the same age as the Rins complex, the 1.8 billion. So it's got zircons of the age of these granites in it. It's also got some old ones which match what we had, an old granite, old Louisian type thing, 2.5, 3 billion years old, and some younger stuff. What's important that we have this old stuff. Port Askaig rocks have a lot of old zircons, as well as the 1.8 and younger ones. Yeah, and this is on Laurentia, which is this continent here. And all the samples we've ever taken from Laurentia have old zircons in this area here. Now I go over to Scandinavia and Amazonia first. South America, our prime candidate. The diamictites, the glacial rocks derived from the basement of the old rocks don't have these zircons, don't have the old zircons. And neither do Swedish rocks, Norwegian rocks, they're mostly not Norwegian. So the detrital zircon storing is telling us something different. It's saying it's likely to be Laurentian, i.e. North American. So it's pointing more towards Rockall, Labrador, all those sorts of areas. But we said that they weren't right. So I'm still in a quandary. So I tried to make a map of where the Port Askaig was 700 million years ago. So that's the yellow. This is the Port Askaig from Connemara to Shetland there, and we're in the middle of it. There's Rockall. I've taken away the Atlantic Ocean. And there's Greenland, and there's Labrador. This is a thing called the Grenville Front, which is a metamorphic zone. One point, you need to worry about that. I won't really get into that. But the Baltica is over here, and these are the remaining bits of glaciated rocks we see around here. And these are the ones that don't have any zircons in them from the old stuff. This one does, this one doesn't, this one does. We do here. So we think the Port Askaig was in this sort of deeper centre here, but we know from lots of evidence that to the southeast of us here in Scotland, in Islay, underneath the Midland Valley of Scotland, there's some very old rocks that are probably this age. And they occur underneath Tyrone, they occur underneath Mayo in Lochnafuig, they occur deep underneath Newfoundland. So there's a whole string of rocks that we don't see today. They're buried and hidden. And they're to the southeast of Islay. So I'm kind of thinking maybe that's where these rocks have come from, and we don't see them anymore. So I drew a little map. Yeah, this is the Port Askaig in here. And then I drew a little map saying, well, look, during the ice, could this have been what it looked like? From the ice sheets to the north and south, maybe there was ice on this little ribbon microcontinent of the Midland Valley, and it put ice to the, so ice moved to the up, different direction to the sands coming from the other place. So it's a sort of model that tries to explain all those conundrums. Maybe complete rubbish. It may not survive publication, but it's trying to explain these conundrums between the chessboard albite and the push directions from the thing and all that sort of stuff. So it could be Amazonian, could have come this way, could be Baltican, but the zircon stuff says unlikely. The end of the Ice Age. This is just why we haven't got a capped carbonate. We've got mainly sandstones. This is the thing with my purple granite in it, and it's nothing like the beautiful capped carbonate that Paul Hoffman was talking about. So we've got a different story here, yeah, and it's very different to the snowball capped carbonate story. I could spend another hour talking about that. I'm not going to, but it's just there isn't a capped carbonate in this traditional sense here. We do have carbonates. We have these stromatolites, but they're not the carbonates that Paul Hoffman describes. Just to go back quickly to the age of the Port Askaig, we have all sorts of evidence of the age of the ironstones, the zircon story, some other things to strontium and other features, and also some brand new work that I'm doing with a guy called Elias from London on detrital zircon, the youngest grain. He now can sample enormous numbers of zircons. If you can find the youngest grain, it tells you what the maximum depositional age was of the rock. And we found that each of these members successively younger and younger zircons of exactly the right age for the Sturtium. And we think this Franklin large igneous province was maybe clouds of ash and dust, and some just settled out into the Port Askaig. Because we just get 1 or 2 grains of these very young stuff. It's swamped by all the 1.8 billion year old zircons, but we get these. Now we can do such good analysis. We can actually, and the fact that they all line up younger, older, younger, as you go through the stratigraphy, it's like the law of superposition, means that they're probably realistic, and it tells you really what the age of these rocks are, which is great for the golden spike, because that's the bit's missing. We need the age, yeah? And we think we've got it. So we don't think, I'm going to go why it's not Marinoan. We don't think it's Marinoan, although some people do. So there we are. There's back to that picture with the thing, and ta-da! Maybe it's I, maybe it's no, as Kenny Dalradian said. Maybe this is the place to have our golden spike on the Garvellachs. Won't be Islay, it have to be the Garvellachs. Islay's a break, Garvellachs is a nice sequence, so we might have a little disc and a golden spike. But it's really in the hands of these guys. This is the Cryogenian subcommission of the International Geological Union of Subcommittee Stratigraphy. And you've just probably seen in the news recently about whether they're going to have an Anthropocene or not. Yeah, and they decided these are the sort of committees that go out and visit these places and look at all the evidence, and people pitch it, and it's like Dragon's Den, you have to pitch it. And so we're pitching, and the detrital zircon work that we've been doing with Elias is another little bit of icing, we think. We need to get these guys back. Yeah, this was 2016, they were last out there. And we had a subgroup came two years, last year. So, yes, so thank you. These are the pictures of these rocks. You can have a look at not that you can see chessboard albite in them, but these are, if you want to see, if you hadn't seen a Port Askaig granite before, have a look at these. Some of the students said they were possibly interested in a book.